exponential functions and logarithmic functions are inverses of each other. So because when we graph an exponential function, exponential functions have horizontal asymptotes, for logarithmic functions, they're going to have vertical asymptotes. And for any parent function, the asymptote is going to be the line x equals 0 instead of y equals 0 like it was for an exponential function. So for all log functions, all parent log functions, the vertical asymptote is at x equals 0, which means when we graph these log functions, they're going to get closer and closer to that vertical line, in this case the y-axis, without ever actually touching it. Because there's going to be a vertical asymptote for log functions, the domain is going to be limited based on where the asymptote is. So in this case, for each of these graphs, the domain is x is greater than 0. And the range is going to be all real numbers. Notice that it's flip-flopped from what an exponential function was. For exponential functions, the domain was always all real numbers, and the range was limited based off of our horizontal asymptote. That's because log functions and log functions and exponential functions are inverses of each other. Let's do 4 graphs together. The first graph says graph y equals log base 3 of x. The first thing that I do when I'm graphing these is I rewrite it as an exponential function. So if I was going to rewrite this as an exponential function, instead of y equals log base 3 of x, it would say my base is 3, my exponent is y, and that equals x. So because x is isolated instead of y, it's actually easier to plug in numbers for y. It's like treating y like the independent variable instead of x. So I'm going to plug in my 5 favorite numbers into the y values instead of into the x values. So when I do that, I get 3 to the negative second power equals x, or x equals 1/9. I get 3 to the negative first power equals x, or 1/3. 3 to the 0 power is 1, and 3 to the first power is 3, and 3 squared is 9. So even though I kind of worked backwards, I plugged numbers in for y instead of in for x, when I graph these, I still graph the x first. So this is the point 1/9 negative 2, or my x value is 1/9 and my y value is negative 2. My x value is 1/3, my y value is negative 1. My x value is 1, y value 0. Now the point 3, 1 and the point 9, 2. Remember, for log functions, they each have a vertical asymptote. And this is a parent function with a base of 3. So my vertical asymptote is at x equals 0, or the y-axis. So my domain is limited. All the numbers are to the right, or all of my points are to the right of the y-axis. So x is greater than 0. And my range is all real numbers. I could have plugged in any number for y that I wanted to. Oops. Let's try another example, this time with a base of 1/2. So I'm going to rewrite that as an exponential equation since we're more familiar with exponential equations instead. So instead of y equals log base 1/2 of x, I'm going to say my base is 1/2. My exponent is y, and that equals x. So once again, I'm going to plug in values for y instead of in for x. So I'm going to take 1/2 to the negative second power to get 4. 1/2 to the negative first power to get 2. 1/2 to the 0 power, which is 1, 1/2 to the first power, which is 1/2, and 1/2 squared, which is 4. Sorry, 1/4. All right, once again, our asymptote, this is right here at the y-axis, or x equals 0. So because log functions have vertical asymptotes, the only way our asymptote changes from x equals 0 is if we're moving the function right or left. Moving it right or left will change where that asymptote is. So our asymptote is at 0, which means all of our points are going to get really close to x equals 0 without touching it. And when I graph these, so let's say I've got 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2, and they would have just kept getting closer and closer to that vertical asymptote. So our domain, because the vertical asymptote was at 0, is x is greater than 0, and our range is all real numbers. So what happens when we start adding in transformations? What I actually think is the easiest way to graph these, this might be a little unique, is I'm going to start just by doing the parent function, log base 2 of x. Or if I rewrite that as an exponential, that would say 2 to the power of y equals x. So just like I have been doing, I'm going to plug in numbers for y. So when I plug in -2, 2 to the -2nd power is 1/4. 2 to the -1st power is 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. So these are the 5 points I'm starting with. Then what I'm going to do is I'm going to apply these transformations. Adding to the x moves the graph left 3, and adding outside moves the graph up 1. So I'm going to move each of these points, each of these 5 points to the left 3 or up 1. I can physically graph the original and then move each one left 3 and up 1. Or you can just change the points by subtracting 3 to all the x's to move them left 3. And adding 1 to all the y's to move it up 1. Move the graph up 1. So that's what I'm going to go for, just so that my graph doesn't look crowded by doing both graphs on here. But because this graph moved left 3, that means that my asymptote, instead of being at 0, is going to be here at -3. And then when I rewrite each of these points, oh, goodness sakes. Well, good thing I remember what they were. So when we had 1/4, -2, 1/2, -1. This was for the equation 2 to the power of y equals x. That was the parent function before we applied the transformations. I guess I can press undo here. Let's do that instead, actually. Oh, I ran out. Bummer. Okay, let's do that again. So log base 2 of x, so equals y, is 2 to the power of y equals x. So the points again were 1/2 -2, nope, 1/4 -2, 1/2 -1. If I plug in 0, I get 1. If I plug in 1, I get 2. It's hard for me to think backwards after so many years of plugging in for x instead of for y. So there were the points that we had gotten. Then I'm going to move each one of these left 3 and up 1. And so I said to do that, I'm going to subtract 3 from each of the x values. And I'm going to add 1 to each of the y values. So when I do that, when I take 1/4 minus 3, that's -2, brain, When I add 1 to negative 2, when I subtract 3 from 1/2, when I add 1 to negative 1, when I subtract 3 from 1 and add 1 to 0, when I subtract 3 from 2 and add 1 to 1, and subtract 3 from 4, add 1 to 2. So these would be my 2 points after the transformation. So we're getting really close to that asymptote, just like we should. My domain is based on that asymptote. All the points are to the right of negative 3, so x is greater than negative 3. And my range is all real numbers, like it is for all log functions. All right, one more of those. So I'm going to start this one just like I started the last one. I'm going to ignore this transformation of right 3. Although what I know is that my asymptote is now going to be over here at 3 instead of at 0. My parent function has a base of 1/3. So y equals log base 1/3 of x, or if I rewrite that, the base is 1/3, the exponent is y, and that equals x. So once again, I'm going to plug in for y to figure out what x is. So when I plug in, let me use a different color here. -2, I get 9. -1, I get 3. 0, I get 1. 1, I get 1/3. 1/3 to the first power is 1/3, and 1/3 squared is 1/9. So those are the 5 points I'm starting out with. Now I'm going to move them all to the right 3. And to move them all to the right 3, that changes the x values by 3. So I'm going to add 3 to all the x values. I'm not changing the y values because I'm not moving up or down at all. So my new points are going to be 12, -2, 6, -1, 4, 0, 3 and 1/3, 1, and 3 and 1/9, 2. So 12 -2s off the graph, but we can kind of estimate it there. 6, -1, 4, 0, 3 and 1/3, 1, 3 and 1/9, 2. So we're getting really, really close to 3 without touching it. So my domain, all of those values are greater than 3 for x, and my range is all real numbers.